This video is going to continue our work with L'Hospitals Rule and show you some more advanced versions of it. So we saw in the previous video that L'Hospitals Rule works directly when you have either 0 over 0 or infinity over infinity. Then we saw an example where we had a 0 times infinity case, and we were able to use some algebra to make it work out. Next, we're going to look at also cases where we have infinity minus infinity. We're going to look at cases where you have 1 to the infinity. We're going to look at cases where you have infinity to 0 and 0 to the 0. Now all of those together, those are called indeterminate forms. And the reason they're called that is we cannot determine what the answer is. Let me explain what I mean by that. Let's look at just for the last one. We have 0 to the 0. Now normally 0 to anything is always going to give you back to 0. On the other hand, normally something to the 0 power is always going to give you 1. And so the thing is, when you have 0 to the 0, you have two conflicting rules about which one the answer should be. That's why we can't determine what the correct answer is, and we're going to use L'Hospitals Rule in order to work it out. Now, we'll look at these 4 examples here. The first one, if you try plugging in 1 from the right, you're going to have 1 over 0, or really to be more accurate here, you'd have infinity minus infinity here. Well, the infinity minus infinity case is actually one of the trickier examples because there is not one right thing that you're going to do that will always work. However, it is going to come down to algebra of some way to get the answer. And in this particular case, what we can do is we can use algebra to combine the fractions together into a single fraction. There we go, write the x minus 1 first on the bottom here. And once we've done this, then we would end up having a 0 over 0 case. So then we can use L'Hospitals Rule. The derivative of ln x is 1 over x. Derivative of minus x is minus 1. And the 1 goes to 0. On the bottom, we're going to have to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. And if you plug in 1 here, it's still going to be 0 over 0. So I will apply L'Hospitals Rule again here. And see, derivative of 1 over x is negative 1 over x squared. Derivative of ln x is 1 over x. The derivative of this thing, well, maybe I should simplify it before taking derivatives. That's going to be 1 minus 1 over x. So then that's going to become plus 1 over x squared. And at this point in time, we can go ahead and plug in 1 everywhere. And we're going to get negative 1/2. So in this particular case, infinity minus infinity is negative 1/2. Okay. Next one up, we have x goes to 0 of x to the x. That means we have 0 to the 0 here. Well, turns out that for any of these ones that have exponents, there is a certain procedure that you're going to want to use on them, and they're going to involve logarithms. So what we're going to do is we're going to go ahead and apply the logarithm to our function. So we're going to say if y equals x to the x, then ln y is ln x to the x. Then we're going to go ahead and use algebra to bring the x down. Right? Exponents become coefficients here. And then we're going to take limits of both sides. So the limit as x goes to 0 of ln y is the limit as x goes to 0 of x ln x. Now conveniently, we actually did this exact limit on the previous video here. And that limit is going to give us 0. And now that we have that limit, you might say, well, the answer to the problem is 0, but it's not. This is the limit of the ln of the function. And what you need to remember is that if you take y is the same as e to the ln of y, and so that means the limit that we're trying to find here is going to be e to whatever number we got. And so the actual answer to this problem is not 0, it is 1. But you still are using logarithms to get the answer. Now we have 2 more videos here, both involving the exponential rule here. So in this case, as you go to infinity here, the base goes to 1, the exponent goes to infinity. So we go ahead and say, okay, that's what we have there. We need to go ahead and simplify it. So we're going to apply logarithms as we did before. ln y is ln 1 plus 1 over x to the x. Bring down the x in front. As again, this is why we use logarithms, so that we can use that property to get rid of the exponent part. And then if we look at infinity here, we'd have the infinity times 0 case. Oops, that should not be infinity there. We should have the infinity times 0 case. So we're going to go ahead and turn that into a fraction. Generally easier to move the x to the bottom. Take derivatives. Derivative ln of something is going to be 1 over that something times the derivative of what's inside, negative 1 over x squared, over the derivative of the bottom, negative 1 over x squared. These actually cancel out. And then as you go to infinity, this part goes to 0, and you're going to have just 1 here. But again, that's not the final answer. The final answer, we take e to that power, e to the 1, or just e. In fact, it's possible that you saw this as a definition for the number of e in one place or another. That's commonly how we do it. And you might say, where does this come from? Little side note here is that this is basically, let me use a different color. This is basically the compound interest formula. So the idea is you take the compound interest formula, but you put a bunch of 1s everywhere. And if you let go to infinity, so you're compounding it infinitely many times, that's where the number e comes from. In case you were curious about that, that's where the origin of e is, from compound interest here. Regardless, we're still using our LHospitals rule with our natural logs to get our answer. One more example here. We'll go ahead and do y equals ln x to the 1 over x. I guess technically we should have tried it first. This would be an infinity to the 0 case. We do need to make sure that it's one of the indeterminate forms. If it is not one of the indeterminate forms, then our whole process will not work. So we apply our logarithms here, and we would get 1 over x ln of ln x. And if we take it, limit x to infinity of this thing, this would be an infinity over infinity case. So we're going to go ahead and take derivative top and bottom. Derivative ln of something goes to 1 over that thing times the derivative of what's inside. The derivative of the bottom is just 1 here. And now as we go to infinity, these are infinities in the bottom. These are going to go to zeros here. So 0 times 0 over 0 is 0. And so that means the original problem has an answer of e to the 0, or just 1 for this limit. So again, these are definitely trickier limits here, but whenever you're given a new limit, see if it's in one of these formats up here. Any of these indeterminate forms can be used in some way for LHospitals rule by playing around with it. If it's not one of those forms, then you have to use one of the techniques that we learned previously for finding limits.